So, what could a casual stroll possibly have in common with Goku's Kamehameha wave? Well, believe it or not, they're both governed by the exact same secret language, the physics of motion. And today, we're going to crack that code. We're diving into the rules that control literally every move in the universe. All right, let's kick things off with a little brain teaser. Picture this. You go for a run, you cover a full mile, your heart's pounding, you're sweating, but a physicist would look at you and say, nope, you haven't gone anywhere at all. How is that even possible? It sounds crazy, right? Well, hang on, because the answer to that question is going to unlock the first major secret of motion for us. So the key to solving that riddle is all about learning the language of motion. You can think of it like a code, just a few key words to learn. And once you get them, I promise, the way you see the world moving around you is going to change. The field we're talking about is called kinematics. Basically, it's the study of how things move without getting all bogged down in why they move. We're just describing the motion. Where is it? How fast is it going? Which way is it headed? We're going to leave the why, all the forces and gravity stuff, which is a whole other topic called dynamics. We'll save that for another time. Right now, it's all about the description. Okay, so at the very core of this language are two super important ideas, vectors and scalars. Now, a scalar, that's the easy one. It's just a number, a magnitude. Think 10 kilograms or 25 degrees. Simple. But a vector adds one tiny but absolutely crucial piece of information, direction. So it's not just 10 miles per hour, it's 10 miles per hour north. And trust me, that one little word changes absolutely everything. So let's look at some examples. Things like velocity and displacement, those are vectors. Direction matters a ton. But things like speed and distance, purely scalars. I mean, you'd never ask, what's the direction of my mass, right? It's just a number. Getting this difference down is honestly the key to understanding everything else we're going to talk about. Okay, so this whole vector versus scalar thing, how does it actually play out in the real world? Well, let's start by looking at the difference between the journey itself and your final destination. Okay, look at this. Imagine you're walking from point P over to point Q. You've got two choices. You can take this long, scenic, winding path, or you can just go straight there. Now, obviously, one path is way longer than the other, but a physicist might argue that in one very specific way, they are exactly the same. How on earth can that be true? This right here, this is the huge difference between distance and displacement. Distance is a scalar. It's the total ground you covered, right? Every single step on that winding path gets counted. But displacement, that's our vector, and it only cares about one thing, the straight line path from where you started to where you ended. It's literally the difference between how far you've traveled and how far you are from where you started. Okay, let's put this to the test with a fun one. Mario here does a perfect lap around the track. His cart's odometer is definitely going to show he traveled a pretty long way. But based on what we just learned, what's his total displacement? The answer is 0, a big fat 0. Why? Because displacement only cares about the change from your starting point to your finishing point. And since Mario ended up in the exact same spot he started, his displacement is 0. He definitely traveled a distance, but his overall position never changed. And hey, that's the answer to our riddle about the runner. All right, so we've got location down. We totally get the difference between distance and displacement now. So what's the next logical question? Well, how fast are we going? And to answer that, we need to bring time into the mix. And that brings us to velocity. Now, here's the key thing to remember. Velocity is all about how fast your displacement is changing. And since we already know displacement is a vector, well, that means velocity has to be a vector too. It's not just how fast you're going, it's how fast you're going and in what direction. And of course, it has a scalar buddy, speed. Speed is easy. It's just the number you see on your car's speedometer. Your car has no clue if you're driving north, south, east, or west. It just tells you how fast your wheels are turning right this second. Okay, now this is where things can get a little weird, so stick with me. How can something moving at negative 20 meters per second actually have more speed than something moving at positive 10? Well, it's because speed doesn't care about the negative sign. Speed is just the raw number, and 20 is bigger than 10. Simple. Velocity, on the other hand, does care. On a number line, negative 20 is definitely less than 10. All that negative sign is doing is telling us the direction. It's basically an arrow pointing the other way. Let's make this crystal clear with an example. So you've got Pikachu and Eevee starting in the same spot. Pikachu zooms off with a velocity of positive 20 meters per second. Eevee trots off in the opposite direction at negative 10 meters per second. So, after 10 seconds go by, Pikachu is 200 meters away. And Eevee, she's at the 100-meter mark, but in the other direction. So, what's the total distance between them? Well, since they went in opposite directions, you just have to add up how far each of them went. You've got Pikachu 200 meters one way, and Eevee 100 meters the other way. Put them together, and they're 300 meters apart. See? That negative sign didn't mean Eevee was slower, in a sense. It just told us which way she was going. It was just a signpost. Okay, we're almost there. Just one last piece of this motion puzzle. We know how to talk about position and moving at a steady pace. But let's be real, motion is hardly ever constant. So what do we call it when things speed up, or slow down, or even just change direction? That, my friends, is acceleration. And what's really cool is how consistent the logic is here. Just like velocity was the change in displacement, acceleration is the change in velocity. It's a perfect pattern. And that means anytime your velocity changes, whether you speed up, slow down, or turn a corner, you are accelerating. And you guessed it, since velocity is a vector, acceleration has to be a vector too. And the rules for how this works, they're actually super simple. If your velocity and your acceleration are pointing in the same direction, you speed up. It's like getting a push from behind. But if they're pointing in opposite directions, you slow down. Think of it like running into a strong headwind. So check this out. Let's look at the car scenarios. If a car is traveling east, but it's hitting the brakes, its velocity is still pointing east, but its acceleration has to be pointing west, fighting against that motion. Now flip it around. If the car is going west and slowing down, its acceleration must be pointing east. It all comes down to a simple question. Are the two arrows working together, or are they fighting each other? Okay, so let's do a super quick recap of everything. Vectors have direction, scalars are just numbers. Got it. Distance is the total path you took, displacement is just the straight line from A to B. Easy. Velocity is speed with a direction, and speed is just the number on the dial. And finally, acceleration is any change in that velocity. That's it. That's the secret language of motion right there. So, I'll leave you with one final little pop quiz to see if you've got it. A car is driving west, but the driver is hitting the brakes and slowing down. So, which direction is its acceleration pointing? Think about it. The answer is right there in the simple rules we just went over. Thanks for tuning in.